What if everything we thought we knew about the universe was just the tip of the iceberg? Picture this: vast, invisible threads weaving through the cosmos, shaping galaxies, bending light, and holding the very fabric of reality together. These mysterious forces belong to what scientists call the cosmic dark matter era, a period shrouded in enigma and wonder. Today, we're diving into 25 of the most baffling mysteries of this hidden cosmic era. From the origins of dark matter to its invisible influence on the universe, each mystery will take us deeper into the unknown. Why does dark matter refuse to interact with light? Could it be the key to understanding the birth of galaxies? And what secrets does it hold about the fate of our universe? By the end of this journey, you'll not only grasp the scale of these questions, but also see why they're some of the greatest puzzles in modern science. So, buckle up and prepare to explore the unseen forces that are rewriting our understanding of the cosmos. Let's uncover the 25 mysteries of the cosmic dark matter era. As we begin our journey into the mysteries of the cosmic dark matter era, let's turn our attention to the very foundation of this cosmic puzzle, the origins of dark matter. What exactly is this enigmatic substance, and where did it come from? To understand dark matter, we must first look back to the early moments of our universe. One of the leading theories suggests that dark matter was born in the aftermath of the Big Bang, the explosive event that set the universe into motion. During this time, as matter and energy began to take shape, it's believed that dark matter particles formed alongside the more familiar matter we see today. But here's where the mystery deepens. Unlike ordinary matter, which is made up of atoms and interacts with light, dark matter seems to operate by entirely different rules. Some scientists propose that dark matter could consist of exotic particles predicted by theories like superstring theory, which suggests that the universe is made up of tiny, vibrating strings of energy. However, despite decades of research and countless experiments, we still haven't directly observed or identified what dark matter truly is. Its origins remain one of the most profound questions in science, a cosmic riddle that challenges our understanding of the universe itself. As we continue to explore this mystery, each theory brings us closer to unraveling the secrets of the invisible force that shapes our cosmos. Now turning to the next layer of this cosmic enigma, let's explore one of the most puzzling aspects of dark matter, its invisibility. Unlike the stars, planets, and galaxies we can see, dark matter doesn't emit, absorb, or reflect light. It's completely transparent to the entire spectrum of electromagnetic radiation, from radio waves to gamma rays. This makes it impossible to observe directly with telescopes, no matter how advanced they are. But if we can't see it, how do we even know it exists? The answer lies in its gravitational influence. Dark matter exerts a powerful pull on the visible universe, bending the path of light and altering the movement of stars and galaxies. Scientists call this effect gravitational lensing, where the gravity of dark matter distorts light from distant objects, creating ghostly arcs and rings in the night sky. Additionally, the way galaxies rotate and cluster together gives us clues about dark matter's presence. Stars at the edges of galaxies move much faster than they should if only visible matter were holding them together, hinting at an invisible force at work. By studying these gravitational effects, researchers can map out where dark matter resides, even though it remains hidden from our eyes. It's like trying to find a person in a dark room by tracking their footsteps. We may not see the person, but we can piece together where they've been and what they've done. This indirect detection is the key to uncovering the nature of dark matter, a silent yet dominant player in the cosmic dance. As we continue to probe its mysteries, each observation brings us closer to understanding the invisible threads that weave the fabric of our universe. As we venture further into the shadows of the universe, let's unravel the next layer of this cosmic puzzle, the composition of dark matter. What is it actually made of? Scientists have proposed several leading theories, but the truth remains elusive. One of the most prominent candidates is weakly interacting massive particles, often abbreviated as WIMP. These hypothetical particles are thought to be heavy and interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Another possibility is axions, much lighter particles that could also fit the bill. Axions were originally theorized to solve a problem in particle physics, but they've since become a strong contender for dark matter. Despite these ideas, neither WIMP nor axions have been definitively observed. So, why is it so hard to prove what dark matter is made of? The challenge lies in its minimal interaction with ordinary matter. Unlike the particles you and I are made of, dark matter doesn't collide, absorb, or emit light, which means we can't study it using traditional methods. Instead, researchers rely on indirect evidence such as gravitational effects to infer its properties. There's also the possibility that dark matter could be made of something entirely different, like sterile neutrinos or even exotic particles we haven't yet imagined. Each hypothesis opens new doors but also raises more questions. With every experiment that fails to detect WIMP or axions, scientists are pushed to think outside the box, exploring even more unconventional ideas. The search for dark matter's composition is like trying to identify a ghost by its footsteps. We know it's there, but its true nature remains just out of reach. As we continue to probe the cosmos, each discovery, even the ones that don't pan out, brings us closer to understanding this invisible force that shapes our universe. Now turning to the next layer of this cosmic enigma, let's explore how dark matter is spread across the vast expanse of the universe. Unlike ordinary matter, which clumps together to form stars, planets, and galaxies, dark matter is thought to be distributed in a vast, intricate web that stretches across the cosmos. This cosmic web acts like a scaffold, guiding the formation of the largest structures we observe today: galaxies, galaxy clusters, and even superclusters. Scientists believe that shortly after the Big Bang, tiny fluctuations in the density of dark matter began to grow. Over billions of years, gravity pulled these denser regions together, creating the seeds for galaxies and galaxy clusters. Without dark matter's gravitational influence, the universe as we know it would look entirely different. Its presence explains why galaxies spin faster than they should, and why galaxy clusters hold together despite the immense forces at play. But how do we map something we can't see? Through clever observations and simulations, researchers have been able to infer dark matter's distribution. They study how it bends light from distant objects, a phenomenon known as gravitational lensing, and compare these observations to computer models of the universe. These efforts reveal that dark matter isn't spread evenly. Instead, it forms dense halos around galaxies and filaments that connect them, creating a cosmic network. Yet, questions remain. Why does dark matter cluster in some areas more than others? And how does its distribution influence the evolution of the universe over time? As we continue to map this invisible framework, each discovery brings us closer to understanding the hidden architecture of the cosmos. The mystery of dark matter's distribution isn't just about where it is, it's about how it shapes the universe we call home. Shifting our focus to another fascinating aspect of dark matter, let's explore the mysterious phenomenon of dark matter halos. These invisible structures surround galaxies like vast, ghostly cocoons, extending far beyond the visible edges of the galaxies themselves. While we can't see these halos directly, their presence is felt through their immense gravitational influence. Stars and galaxies within these halos move in ways that defy expectations based on the visible matter alone. For example, stars at the outer edges of galaxies orbit much faster than they should if only the visible matter were pulling on them. This discrepancy was one of the first clues that something invisible, dark matter, was at play. Scientists believe these halos form as dark matter gathers around galaxies, creating a gravitational framework that holds everything together. Without these halos, galaxies might not have formed as they did, and they certainly wouldn't stay intact. The size and density of dark matter halos vary, with some being more massive than others. Interestingly, the shape of these halos can also differ, often resembling flattened spheres or more irregular forms. But why do these halos exist, and how do they maintain their structure? One theory suggests that dark matter particles interact very weakly with each other and with ordinary matter, allowing them to form stable, long-lasting halos. Another intriguing aspect is how these halos influence the motion of galaxies within galaxy clusters. The gravitational pull of these halos can dictate how galaxies move and interact, shaping the large-scale structure of the universe. As we study these halos, we uncover more questions than answers. What determines the size and shape of a dark matter halo? How do they evolve over time? And what role do they play in the universe's ongoing expansion? Each discovery about dark matter halos brings us closer to understanding the unseen forces that shape our cosmos. The mystery of these halos isn't just about their existence, it's about how they silently govern the motion of stars and galaxies, weaving the intricate dance of the universe. Now turning to the next puzzle in the cosmic tapestry, let's dive into the mystery of dark matter's role in galaxy formation. Galaxies, those vast collections of stars, gas, and dust, are the building blocks of the universe. But how did they come to be? Scientists believe dark matter played a critical part in this process. In the early universe, dark matter's gravitational pull helped gather ordinary matter into dense regions. Over time, these regions collapsed under their own gravity, forming the seeds of galaxies. Without dark matter, the universe might have remained a diffuse soup of particles, never coalescing into the structures we see today. The exact mechanisms, however, remain shrouded in mystery. For instance, how did dark matter's distribution influence the size and shape of galaxies? Why do some galaxies form spirals while others become ellipticals? One leading idea is that dark matter halos, those vast invisible structures we discussed earlier, provided the gravitational scaffolding for galaxies to form. Yet, questions persist. Did dark matter particles interact with ordinary matter in ways we're not yet aware of? Could there have been additional forces at play during the early stages of galaxy formation? As we study this intricate relationship, we're reminded of just how much we still have to learn. The role of dark matter in galaxy formation isn't just a scientific question, it's a window into understanding the very fabric of our universe. With each discovery, we inch closer to unraveling the secrets of how galaxies came to be, and how dark matter silently shaped the cosmos we call home. As we venture deeper into the mysteries of dark matter, let's explore a question that has puzzled scientists for decades. How does dark matter interact with regular matter? This interaction, or rather the lack of it, is one of the most baffling aspects of dark matter. Unlike ordinary matter, which interacts through electromagnetic forces, allowing us to see, touch, and feel it, dark matter seems to operate in a completely different way. It doesn't emit, absorb, or reflect light, and it barely interacts with the protons, neutrons, and electrons that make up the atoms of the visible universe. The only force that clearly connects dark matter to the rest of the cosmos is gravity. It's this gravitational pull that allows us to detect dark matter indirectly by observing its effects on stars, galaxies, and even the bending of light, known as gravitational lensing. But why is this interaction so minimal? One leading theory suggests that dark matter particles are what scientists call weakly interacting massive particles, or WIMPs. These hypothetical particles would only interact with ordinary matter through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Another idea is that dark matter might interact with itself in ways we don't yet understand, creating a hidden subatomic world that operates parallel to our own. Understanding the nature of these interactions is crucial because it could unlock the secrets of dark matter's composition and behavior. If we can determine how dark matter connects with regular matter, even in the faintest ways, we might finally find clues to its true identity. This knowledge could also shed light on how dark matter shaped the universe, influencing everything from the formation of galaxies to the distribution of cosmic structures. The search for these interactions is ongoing, with experiments like underground detectors and particle colliders trying to capture even the faintest signal. Yet, so far, dark matter continues to elude us, maintaining its enigmatic distance from the familiar world of atoms and light. As we study this cosmic puzzle, we're reminded that the universe is full of mysteries waiting to be uncovered. The question of how dark matter interacts with regular matter isn't just a scientific challenge, it's a doorway to understanding the very fabric of reality itself. Now, shifting our focus to a fascinating yet elusive theory, let's explore the mystery of dark matter annihilation. What if dark matter particles could collide and annihilate each other, releasing energy in the form of gamma rays? This idea has captivated scientists as it offers a potential way to detect dark matter indirectly. The theory suggests that when two dark matter particles meet, they could destroy one another, transforming their mass into gamma rays, high-energy light that we can observe with specialized telescopes. If this process occurs, it could leave behind a unique signature in the universe's gamma ray background, serving as a telltale clue to dark matter's presence. However, despite extensive searches, concrete evidence of such annihilation remains elusive. Why is this the case? One possibility is that dark matter particles are far less abundant or interact much more weakly than we've predicted. Another challenge lies in distinguishing gamma rays produced by dark matter annihilation from those generated by other cosmic sources, such as pulsars or black holes. Scientists have turned to regions dense with dark matter, like the centers of galaxies or dwarf galaxies, to look for excess gamma rays that could signal annihilation. Yet, these observations have not yet provided definitive proof. Some experiments, like the Fermi Gamma Ray Space Telescope, have detected intriguing signals that could hint at dark matter annihilation, but these findings remain inconclusive. The search continues as researchers refine their methods and develop more sensitive instruments to detect these faint signals. Understanding dark matter annihilation could not only reveal the nature of dark matter, but also provide insights into its role in shaping the cosmos. As we delve deeper into this mystery, we're reminded that even the faintest clues can lead to groundbreaking discoveries. The quest to uncover the truth about dark matter annihilation is far from over, but every step brings us closer to unraveling one of the universe's greatest enigmas. Now, as we venture further into the shadows of the cosmos, let's unravel the mystery of dark matter decay. What if dark matter isn't as eternal as it seems? What if, over vast stretches of time, these elusive particles break down into other forms of matter or energy? This idea opens up a fascinating avenue for understanding dark matter, suggesting that it might not be entirely stable. The concept of decay implies that dark matter particles could transform into lighter, more detectable particles, such as neutrinos or even photons, leaving behind traces that scientists could potentially observe. If this process occurs, it could offer a new way to detect dark matter indirectly, much like annihilation. However, detecting such decay is incredibly challenging. The rate at which dark matter decays, if it does at all, is thought to be extremely slow, making it difficult to observe within the span of human lifetimes or even the age of the universe. Another obstacle lies in distinguishing the signals of dark matter decay from those produced by other astrophysical processes. For example, cosmic rays or the interactions of regular matter can produce similar particles, muddying the waters for researchers. To tackle this challenge, scientists are focusing on environments where dark matter is densely concentrated, such as the centers of galaxies or galaxy clusters, where the likelihood of detecting decay products might be higher. Experiments like Xenon and LUX, designed to detect rare particle interactions, are also searching for signs of dark matter decay, though no definitive evidence has been found yet. The search for decay is further complicated by the fact that we don't yet know the exact properties of dark matter, making it hard to predict what its decay products might look like. Despite these hurdles, the possibility of dark matter decay remains an intriguing area of research, offering a potential window into the nature of these invisible particles. If proven, it could reshape our understanding of dark matter's role in the universe and its ultimate fate. As we continue to probe this mystery, we're reminded that even the most persistent enigmas of the cosmos may hold clues that one day will bring us closer to uncovering the truth. Now shifting our gaze to the heart of cosmic darkness, let's explore the intriguing relationship between dark matter and black holes. Could these two enigmatic entities be more connected than we realize? Black holes, known for their immense gravitational pull, devour everything that comes too close, including light itself. But what about dark matter? Could it, too, fall into the abyss of a black hole, fueling its growth? Some scientists believe that dark matter, being influenced by gravity, could indeed be consumed by black holes, potentially adding to their mass over time. This idea suggests that dark matter might play a role in the growth and evolution of black holes, particularly in the early universe. However, the interaction between dark matter and black holes isn't one-sided. Could dark matter itself be involved in the formation of black holes? One theory proposes that dense clumps of dark matter, known as dark matter halos, could collapse under their own gravity, forming primordial black holes. These black holes, born from the shadows of dark matter, could have been among the first to exist in the universe. Yet this theory remains speculative, as we lack direct evidence to confirm it. Another fascinating question is whether dark matter could alter the behavior or structure of black holes. For instance, if dark matter particles interact weakly with regular matter, they might accumulate around black holes, creating a sort of dark matter halo that could influence the black hole's properties. This could potentially affect how black holes emit radiation or even how they merge with other black holes. Despite these intriguing possibilities, the relationship between dark matter and black holes remains shrouded in mystery. Detecting such interactions is incredibly challenging, as both dark matter and black holes are invisible to traditional observation methods. Scientists rely on indirect clues, such as the gravitational effects on nearby stars or the radiation emitted by matter falling into black holes, to piece together this cosmic puzzle. As we delve deeper into this mystery, we're reminded that the universe often hides its most profound secrets in the interplay between its darkest elements. The connection between dark matter and black holes could hold the key to understanding not only their nature but also the broader workings of the cosmos. And with that, we're ready to uncover the next layer of the cosmic dark matter era, where even deeper mysteries await. Now venturing further back in time, we step into the earliest moments of the cosmos to uncover the role dark matter played in shaping the universe as we know it. Shortly after the Big Bang, the universe was a seething, chaotic expanse of energy and particles. Amid this primordial soup, dark matter was already at work, silently influencing the course of cosmic evolution. Unlike ordinary matter, dark matter doesn't interact with light or radiation, allowing it to clump together long before stars and galaxies could form. These early clumps of dark matter acted as the scaffolding for the universe, creating gravitational wells that drew in ordinary matter, setting the stage for the first cosmic structures. To understand this pivotal role, scientists turn to the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light which permeates the universe carries imprints of the early universe's conditions, including the distribution of dark matter. Tiny fluctuations in this radiation reveal how dark matter's gravitational pull began shaping regions of higher and lower density, laying the groundwork for galaxies and galaxy clusters to emerge. Without dark matter's influence, the universe might have remained a featureless sea of particles, never giving rise to the complex structures we observe today. But the story doesn't end there. The cosmic microwave background also hints at the ratio of dark matter to ordinary matter in the early universe, helping scientists refine their models of cosmic evolution. These observations suggest that dark matter was not only present but dominant, guiding the universe's expansion and structure formation, yet many questions remain. How exactly did dark matter interact with the rapidly expanding universe, and what can its early behavior tell us about its mysterious nature today? As we piece together these clues, we gain a deeper appreciation for dark matter's foundational role in the cosmos. Its silent influence in the early universe set the stage for everything that followed, from the birth of the first stars to the sprawling galaxies that fill the night sky. With this understanding, we move closer to unraveling the next layer of the cosmic dark matter era, where even more secrets await discovery. Now shifting our focus to the temperature of dark matter, we delve into one of the most intriguing aspects of its nature. Is it cold, warm, or hot? This question isn't just about temperature in the traditional sense, but refers to how fast dark matter particles were moving in the early universe. Understanding this helps us piece together how it shaped the cosmos. Cold dark matter refers to particles that moved slowly relative to the speed of light, allowing them to clump together more easily. This slow movement meant that cold dark matter could form dense regions early on, creating the gravitational scaffolding for galaxies and galaxy clusters. Most cosmological models favor this idea because it aligns well with the large-scale structures we observe in the universe today. Warm dark matter, on the other hand, suggests particles that moved at intermediate speeds, not as slow as cold dark matter, but not as fast as hot dark matter. This would have led to smaller clumps and smoother structures in the early universe, potentially influencing the formation of smaller galaxies and star systems. While less commonly discussed, warm dark matter offers an alternative explanation for certain observed phenomena, such as the distribution of dwarf galaxies. Hot dark matter involves particles moving at speeds close to the speed of light, making it difficult for them to clump together effectively. If dark matter were hot, it would have spread out more evenly, delaying the formation of cosmic structures. This scenario doesn't align as well with what we see in the universe today, which is why it's considered less likely. The temperature of dark matter isn't just a theoretical curiosity, it has real implications for how the universe evolved. Cold dark matter's ability to form dense clumps early on provided the foundation for galaxies to assemble, while warmer or hotter forms would have altered this process significantly. By studying the temperature of dark matter, scientists can refine their models of cosmic evolution and gain insights into how the universe grew from its chaotic beginnings into the intricate web of galaxies we see today. As we continue to explore this mystery, one thing is clear: the temperature of dark matter holds the key to understanding its role in shaping the cosmos. With each discovery, we move closer to unraveling the full story of this invisible force that silently guides the universe's structure. Now stepping into the realm of cosmic expansion, we explore one of the most profound mysteries, the role of dark matter in the accelerating growth of the universe. While dark energy often takes center stage in discussions about expansion, dark matter's influence cannot be overlooked. Together, these two enigmatic forces shape the fate of the cosmos in ways that continue to baffle scientists. Dark matter, with its gravitational pull, acts as a cosmic glue, holding galaxies and galaxy clusters together. Its presence creates the large-scale structures we see today, forming the backbone of the universe's architecture. However, when it comes to the universe's expansion, dark matter's role becomes more complex. While it doesn't directly drive the acceleration, it sets the stage for dark energy to take over on larger scales. Dark energy, on the other hand, is thought to be the primary force behind the universe's accelerating expansion. Unlike dark matter, which pulls matter together, dark energy seems to push space itself apart. The relationship between these two forces is a delicate balancing act. In the early universe, dark matter dominated, allowing structures to form. But as the universe expanded, dark energy gradually took the lead, driving the acceleration we observe today. Understanding this interplay is crucial for unraveling the mysteries of cosmic expansion. Observations from distant supernova, galaxy surveys, and the cosmic microwave background radiation all point to a universe where dark energy's influence grows over time. Yet, dark matter remains a key player, shaping the conditions that allowed this expansion to unfold. One of the most intriguing questions is whether dark matter and dark energy are fundamentally connected. Some theories suggest they could be manifestations of a single, unified force, while others propose they are entirely separate entities. Solving this puzzle could revolutionize our understanding of the universe's evolution and its ultimate destiny. As we continue to probe these mysteries, the interplay between dark matter and dark energy reminds us of the universe's intricate balance. Each discovery brings us closer to understanding the forces that govern the cosmos, from the smallest particles to the vast expanse of space. With this in mind, we turn our attention to another fascinating phenomenon, the mystery of dark matter clumps and what they reveal about the universe's hidden structure. Shifting our focus to the cosmos' hidden structures, we uncover another captivating mystery, the enigma of dark matter clumps. These dense regions of dark matter, scattered throughout the universe, defy our expectations and offer new clues about the nature of this elusive substance. While we often think of dark matter as a smooth, invisible web weaving through space, the discovery of these clumps suggests a far more intricate and uneven distribution. Observations from gravitational lensing, where dark matter bends light from distant objects, have revealed these clumps in surprising places. Some appear isolated, floating freely in the vast emptiness between galaxies, while others linger near galaxy clusters without being fully absorbed. Their existence challenges the traditional view of dark matter as a uniform, evenly spread component of the universe. One of the most puzzling aspects of dark matter clumps is their persistence. According to early simulations, these clumps should have merged into larger structures over time, smoothing out the universe's dark matter distribution. Yet they remain, defying theoretical predictions. This discrepancy raises critical questions about the properties of dark matter itself. Could it interact more weakly with itself than we thought? Or does it behave in ways that our current models simply cannot explain? The discovery of these clumps also has profound implications for our understanding of galaxy formation. If dark matter is clumpier than expected, it could mean that galaxies formed in more complex and varied ways than previously imagined. This could reshape our theories about how cosmic structures evolve and how dark matter influences the growth of galaxies. As scientists continue to study these mysterious clumps, they're using advanced tools like the James Webb Space Telescope and ground-based observatories to map their distribution and properties. Each new observation brings us closer to understanding why these clumps persist and what they reveal about the hidden structure of the universe. With this intriguing puzzle in mind, we now turn to another fascinating aspect of dark matter, its role in dwarf galaxies and why these small cosmic neighborhoods seem to hold more dark matter than expected. As we venture deeper into the cosmos, another intriguing mystery unfolds, the unusual concentration of dark matter in dwarf galaxies. These small, faint galaxies, often orbiting larger ones like the Milky Way, seem to hold a disproportionate amount of dark matter compared to their visible matter. This unexpected imbalance has left scientists scratching their heads and raises fundamental questions about the nature of dark matter itself. Dwarf galaxies, despite their modest size, are proving to be treasure troves of cosmic secrets. In many cases, the amount of dark matter they contain far exceeds what we'd predict based on their visible stars and gas. To put it simply, these tiny galaxies appear to be dominated by an invisible, massive component that outweighs everything we can actually see. This has led researchers to wonder, why do dwarf galaxies have so much dark matter, and what does this tell us about its behavior? One possible explanation lies in the way dark matter interacts, or rather, doesn't interact, with ordinary matter. Unlike stars and gas, dark matter doesn't collide or clump together in the same way. This means it can accumulate in regions without being disrupted by the gravitational tug of war that shapes visible matter. In dwarf galaxies, this lack of interaction could allow dark matter to remain concentrated, creating these unexpectedly high ratios of dark to visible matter. Another fascinating aspect is how these dwarf galaxies challenge our understanding of galaxy formation. Current models suggest that larger galaxies, like the Milky Way, should have more dark matter because they've had more time to accumulate it. Yet, dwarf galaxies, which are often older and less evolved, seem to defy this expectation. This discrepancy hints that dark matter might behave differently in smaller cosmic environments, or that our models of galaxy formation are missing a critical piece of the puzzle. Observations of dwarf galaxies also provide valuable clues about the properties of dark matter. For instance, the way stars move within these galaxies suggests that dark matter is distributed in a halo-like structure, much like in larger galaxies. However, the density of these halos in dwarfs is far higher, offering a unique opportunity to study dark matter in a more concentrated form. This could help scientists narrow down what dark matter is made of, whether it's WIMP, axions, or something entirely different. As we continue to explore these enigmatic galaxies, tools like the Hubble Space Telescope and upcoming missions like the Nancy Grace Roman Space Telescope are shedding light on their dark matter content. Each new observation brings us closer to understanding why dwarf galaxies hold so much of this mysterious substance and what it reveals about the universe's hidden architecture. With this puzzle in mind, let's turn our attention to the role of dark matter within our own galactic neighborhood, the Milky Way, and how its presence shapes the very fabric of our home galaxy. Now shifting our gaze closer to home, we delve into the mystery of dark matter within the Milky Way. Our galaxy, a vast spiral of stars, gas, and dust, is also deeply woven with this invisible substance, which plays a crucial role in shaping its structure and motion. While we can't see dark matter directly, its presence is felt through the gravitational forces that influence the way stars and gas move throughout the galaxy. One of the most compelling pieces of evidence for dark matter in the Milky Way comes from the rotation curves of stars. As astronomers measure the speed at which stars orbit the galactic center, they notice something peculiar. Stars farther from the center don't slow down as much as expected. In fact, their speeds remain surprisingly consistent, suggesting the presence of an unseen mass exerting a gravitational pull. This mysterious mass is dark matter, forming an invisible halo that extends far beyond the visible edge of our galaxy. The distribution of dark matter within the Milky Way is another area of intense study. Unlike the stars and gas that are concentrated in the galactic plane and spiral arms, dark matter is thought to be spread out in a roughly spherical halo. This halo envelops the entire galaxy, providing the gravitational scaffolding that holds it together. Without this invisible framework, the Milky Way as we know it might not exist. But how exactly does dark matter influence the Milky Way structure? One way is by stabilizing the galaxy's spiral arms. the gravitational pull of dark matter helps prevent these arms from unraveling over time, ensuring the galaxy maintains its graceful spiral shape. Additionally, dark matter's presence affects the orbits of globular clusters and satellite galaxies, which orbit the Milky Way in ways that align with the predictions of a dark matter-dominated system. Interestingly, the Milky Way also offers a unique opportunity to search for dark matter particles. Scientists have set up experiments in deep underground labs, shielded from cosmic radiation, to detect faint signals of dark matter interactions. If dark matter particles pass through Earth, they might interact with ordinary matter in ways that these detectors can capture. While no definitive detections have been made yet, the Milky Way's dark matter halo makes it a prime location for such searches. As we continue to map the Milky Way's dark matter distribution and study its effects, new discoveries are reshaping our understanding of our galactic home. From influencing the motion of stars to holding the galaxy together, dark matter is an invisible yet indispensable part of the Milky Way story. And as we uncover more about its role, we edge closer to solving one of the universe's greatest mysteries. With this deeper understanding of our own galaxy, let's consider how dark matter interacts with another cosmic enigma, black holes, and what their relationship reveals about the nature of the universe. Now shifting our focus to the subatomic realm, let's explore the intriguing relationship between dark matter and neutrinos. These ghostly particles, often called the universe's most elusive messengers, share some striking similarities with dark matter. Both are nearly invisible, barely interacting with ordinary matter, and yet they play significant roles in shaping the cosmos. But could neutrinos themselves be a component of dark matter? This question has sparked intense debate among scientists, leading to fascinating discoveries and new questions. Neutrinos are produced in abundance by nuclear reactions, such as those in the cores of stars or during supernova explosions. Incredibly lightweight and neutral in charge, they can pass through entire planets without leaving a trace. This makes them incredibly difficult to detect, much like dark matter. However, unlike dark matter, neutrinos do interact with matter, albeit rarely, through the weak nuclear force. This slight interaction has allowed scientists to detect them using specialized detectors buried deep underground. One of the key differences between neutrinos and dark matter lies in their mass. While neutrinos have an extremely tiny mass, dark matter is thought to be much heavier. This has led scientists to hypothesize that dark matter could be made up of particles beyond the standard model of particle physics, such as WIMP or axions, rather than neutrinos. However, the possibility that neutrinos could still be a small fraction of dark matter cannot be entirely ruled out. Another fascinating aspect of neutrinos is their ability to change identities as they travel through space, a phenomenon known as neutrino oscillation. This discovery, which earned the Nobel Prize in Physics in 2015, revealed that neutrinos have mass, something previously thought to be impossible. While this mass is minuscule compared to what dark matter is believed to possess, it has opened up new avenues for exploring the connections between these particles and the mysterious dark matter. So, where does this leave us in the search for dark matter? While neutrinos are unlikely to be the primary component of dark matter, studying them could provide valuable clues. For instance, understanding how neutrinos interact with matter and influence cosmic structures might shed light on the behavior of dark matter particles. Additionally, experiments designed to detect neutrinos could be adapted or expanded to search for dark matter candidates, bridging the gap between these two cosmic mysteries. As we continue to probe the secrets of neutrinos and dark matter, one thing is clear: the universe is far more complex and interconnected than we once imagined. Whether or not neutrinos are part of the dark matter puzzle, their study brings us closer to understanding the invisible forces that shape our universe. With new experiments and technologies on the horizon, the answers to these questions may be closer than we think. As we unravel the mysteries of neutrinos, let's turn our attention to another critical aspect of dark matter: the ongoing efforts to detect it directly and the challenges scientists face in this quest. With the enigmatic nature of dark matter in mind, let's dive into the cutting-edge methods scientists are using to detect this invisible substance. Despite decades of research, dark matter remains elusive, but the quest to uncover it has led to some of the most ingenious experiments in modern science. From deep underground laboratories to powerful particle colliders, researchers are leaving no stone unturned in their hunt for this cosmic mystery. One of the most common approaches is the use of underground detectors, designed to shield experiments from the interference of cosmic rays and other background noise. These detectors, often buried in deep caverns or old mines, are equipped with sensitive materials like liquid xenon or germanium crystals. The idea is that if a dark matter particle interacts with these materials, it could produce a tiny signal, such as a flash of light or a small burst of energy. So far, while these experiments have captured some intriguing events, none have been definitively linked to dark matter. Another method involves particle colliders, like the Large Hadron Collider at CERN. These massive machines smash particles together at incredibly high speeds, recreating conditions similar to those just after the Big Bang. Scientists hope that these collisions might produce dark matter particles, which could then be inferred from the energy and momentum missing after the collision. While this approach has led to groundbreaking discoveries such as the Higgs boson, dark matter remains stubbornly out of reach. Astrophysical observations also play a crucial role in the search for dark matter. By studying the movement of stars and galaxies, scientists can map the gravitational effects of dark matter, even if they can't see it directly. Gravitational lensing, where dark matter bends the light from distant objects, provides another way to study its distribution and properties. These methods don't detect dark matter particles themselves, but they offer vital clues about where to look and how it behaves. Despite these efforts, the detection of dark matter has proven incredibly challenging. One reason is that dark matter interacts so weakly with ordinary matter that it's almost like trying to catch a ghost. Another issue is that the signals scientists are looking for are incredibly faint, often buried under a mountain of background noise. This has led some researchers to explore alternative theories, such as the idea that dark matter might not be a single type of particle, but a mix of different particles with varying properties. As the search continues, new technologies and experiments are being developed to improve our chances of detection. For example, next-generation detectors with even greater sensitivity are in the works, and space-based observatories are being designed to study dark matter from new angles. While the answers remain just out of reach, the relentless pursuit of dark matter is driving innovation and deepening our understanding of the universe. Now, as we examine the challenges and breakthroughs in dark matter detection, let's turn our gaze to another fascinating phenomenon: how dark matter bends light from distant objects, creating gravitational lensing effects that reveal its hidden presence. Now shifting our focus to the sky, let's explore how dark matter's gravitational lensing reveals its hidden presence in the cosmos. Gravitational lensing occurs when the immense gravitational pull of dark matter bends the light from distant objects like galaxies or quasars as it travels through space. This bending creates strange and beautiful distortions such as arcs, rings, or multiple images of the same object, offering a unique window into the invisible structure of the universe. One of the most striking examples of this phenomenon is the Einstein ring, where light from a distant galaxy is bent so precisely by a massive object, like a cluster of dark matter, that it forms a complete circle around it. These observations not only confirm the existence of dark matter, but also allow scientists to map its distribution with incredible precision. By studying these distortions, researchers can deduce how much dark matter is present in a given area and how it's clustered across vast distances. Gravitational lensing also helps scientists test theories about dark matter's properties. For instance, some models predict that dark matter should form smooth and diffuse halos around galaxies, while others suggest it might clump together in smaller, denser structures. Observations of lensing effects provide evidence for both scenarios, revealing a more complex picture of dark matter's behavior than previously thought. One of the most fascinating applications of gravitational lensing is its ability to magnify distant objects that would otherwise be too faint to see. This cosmic magnifying glass allows astronomers to study galaxies from the early universe, offering clues about how dark matter influenced their formation and evolution. These observations are helping scientists piece together the role dark matter played in shaping the cosmos as we know it today. As we continue to unlock the secrets of gravitational lensing, new technologies like the James Webb Space Telescope are poised to take this research to the next level. By capturing even more detailed images of lensed objects, these instruments could reveal deeper insights into dark matter's nature and its impact on the universe's structure. While the mystery of dark matter remains unsolved, gravitational lensing has become one of the most powerful tools in our quest to understand it. With every new observation, we're not just mapping the invisible, we're rewriting our understanding of the cosmos itself. This brings us to another compelling discovery, the bullet cluster, where the collision of galaxies provided some of the strongest evidence for dark matter's existence. Stepping into one of the most iconic moments in astrophysics, let's delve into the story of the bullet cluster. This extraordinary collision between two galaxy clusters offered some of the most compelling evidence for dark matter's existence. What makes this event so remarkable is how it allowed scientists to observe the behavior of dark matter in a way that was previously impossible. When these clusters collided, the hot gas within them, made up of ordinary matter, slowed down and piled up in the center due to friction. However, the dark matter components, which don't interact with light or gas, passed right through each other, continuing their motion unaffected. This separation of dark matter from visible matter was a game changer. Using gravitational lensing, astronomers mapped the distribution of mass in the bullet cluster and found that most of it didn't align with the visible gas. Instead, it matched the regions where the galaxies were located, confirming that dark matter must exist independently of ordinary matter. This observation provided a direct and visual confirmation of dark matter's presence, silencing many skeptics and solidifying its place in our understanding of the universe. The bullet cluster also offered insights into dark matter's properties. Its ability to pass through other matter without interaction reinforced the idea that dark matter doesn't engage with electromagnetic forces, making it invisible and detectable only through its gravitational effects. This discovery not only advanced our knowledge of dark matter, but also raised new questions about its nature and how it behaves on cosmic scales. As we examine this pivotal moment in astrophysics, it's clear that the bullet cluster serves as a cornerstone in the study of dark matter. It's a reminder that sometimes the universe provides us with natural experiments that reveal its deepest secrets. With this groundbreaking discovery in mind, we're now ready to explore how dark matter intersects with one of the most fascinating areas of physics, quantum mechanics. As we venture deeper into the cosmos, let's shift our focus to the intriguing intersection of dark matter and quantum physics. Could the enigmatic nature of dark matter find its explanation within the strange and fascinating world of the quantum? Quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales, has revolutionized our understanding of the universe. It describes a realm where particles can exist in multiple states at once, where entanglement connects distant particles instantaneously, and where probabilities replace certainties. But does this framework hold the key to unlocking dark matter's secrets? One of the leading ideas suggests that dark matter could consist of particles predicted by quantum theories, such as axions, hypothetical particles that are incredibly lightweight and interact very weakly with ordinary matter. These particles, if they exist, could solve both the mystery of dark matter and certain puzzles in quantum physics. Another possibility is that dark matter could be tied to the concept of supersymmetry, a theory that proposes every known particle has a heavier, unseen counterpart. Yet, despite these intriguing ideas, no direct evidence has been found to confirm these connections. One of the biggest challenges lies in reconciling dark matter with the standard model of particle physics, which describes the fundamental particles and forces in the universe. Dark matter doesn't fit neatly into this model, leaving scientists to explore theories beyond it. The problem is compounded by the fact that dark matter's interactions with ordinary matter are so weak that detecting it requires entirely new approaches and technologies. Experiments like those using sensitive detectors buried deep underground or powerful particle colliders have yet to yield definitive results. Another layer of complexity comes from the quantum nature of space itself. Quantum mechanics suggests that even the vacuum of space isn't truly empty but filled with fluctuating energy and virtual particles. Could dark matter somehow emerge from this quantum fabric, or could it be tied to the mysterious quantum fields that permeate the universe? These questions push the boundaries of our current understanding and require a blend of creativity and rigorous scientific inquiry. As we explore this frontier, it's clear that the marriage of dark matter and quantum physics is a challenging one. Yet, it's also a fertile ground for innovation, offering the potential to reshape our understanding of both the cosmic and the quantum. With every experiment and theory, we inch closer to answers, reminding us that the universe's deepest mysteries often lie at the intersection of its most profound ideas. Next, we'll delve into how dark matter might connect to another groundbreaking theory, supersymmetry, and what it could mean for our cosmic understanding. Now turning to the captivating theory of supersymmetry, we find another potential key to unlocking the secrets of dark matter. Supersymmetry, often referred to as SUSY, is a groundbreaking idea in particle physics that suggests every known particle in the universe has a heavier, yet-to-be-discovered counterpart. These hypothetical particles, known as superpartners, could hold the answers to many unresolved questions in physics, including the nature of dark matter. One of the most exciting predictions of supersymmetry is that the lightest of these superpartners could be stable and nearly invisible, making it an ideal candidate for dark matter. If this is true, it would mean that dark matter isn't just an anomaly but an integral part of a larger, more symmetrical framework of the universe. Scientists have dubbed this hypothetical particle the neutralino, and it's thought to interact so weakly with ordinary matter that it's incredibly difficult to detect. Despite its elegance, supersymmetry remains unproven. Experiments at the Large Hadron Collider and other particle accelerators have searched for evidence of superpartners, but so far, no definitive signals have been found. This has led some to question whether supersymmetry is the right path or if we need to consider entirely new theories. Adding to the complexity, supersymmetry isn't just a single theory but a family of related models, each with slightly different predictions. This makes testing it a daunting task, as scientists must explore a vast landscape of possibilities. However, the search itself is driving innovation, leading to the development of more sensitive detectors and advanced experimental techniques. Even if supersymmetry isn't the answer, it has already reshaped our approach to understanding the universe. Its ideas have inspired new ways of thinking about particle physics and cosmology, highlighting the interconnectedness of seemingly unrelated phenomena. As we continue to probe the mysteries of dark matter, the pursuit of supersymmetry reminds us that sometimes the journey toward discovery is as important as the destination. Next, we'll venture into the speculative realm of the multiverse and explore how dark matter might connect to the existence of other universes. Shifting our gaze to an even larger cosmic canvas, we now explore the intriguing possibility that dark matter might be linked to the existence of other universes. This concept, known as the multiverse theory, suggests that our universe is just one of countless others, each with its own unique physical laws and properties. Within this framework, dark matter could be a bridge connecting our universe to these parallel realms in ways we are only beginning to imagine. One fascinating idea is that dark matter particles might originate from other universes, leaking into ours through hidden dimensions or cosmic overlaps. If true, this would mean that dark matter isn't just a mysterious substance within our universe, but a remnant of interactions with entirely different realities. Some theorists propose that dark matter could even act as a gravitational glue, subtly influencing the structure of our universe while being anchored to others in the multiverse. However, testing these ideas is incredibly challenging. The very nature of the multiverse makes it difficult to observe or measure, as other universes would likely exist beyond the boundaries of our observable cosmos. Detecting particles or effects that originate from other universes would require technologies far beyond our current capabilities. Additionally, the speculative nature of these theories means that much of the evidence remains purely hypothetical, relying on mathematical models rather than direct observation. Despite these challenges, the multiverse concept has sparked a wave of creativity in cosmology, pushing scientists to think beyond the limits of our universe. It encourages us to consider the possibility that dark matter isn't just a local mystery but a global one, intertwined with the fabric of reality itself. While we may not have the tools to directly test these ideas yet, the pursuit of understanding dark matter through the lens of the multiverse keeps our curiosity alive, reminding us that the universe or multiverse is far stranger and more complex than we can imagine. Next, we'll look ahead to the future of dark matter research and the technologies that could finally bring us closer to uncovering its secrets. Now, looking ahead to the horizon of discovery, we turn our attention to the future of dark matter research and the groundbreaking experiments that aim to unravel its secrets. Scientists around the world are developing advanced technologies and innovative methods to detect and study this elusive substance, pushing the boundaries of what we know about the cosmos. One of the most promising avenues is the use of highly sensitive detectors buried deep underground, shielded from cosmic rays and other background noise. These detectors, like the Xenon and LUX projects, are designed to capture the rare interactions between dark matter particles and ordinary matter. By analyzing these interactions, researchers hope to identify the specific properties of dark matter, bringing us closer to understanding its true nature. In addition to underground experiments, particle colliders such as the Large Hadron Collider are being used to recreate the extreme conditions of the early universe. By smashing particles together at incredibly high energies, scientists aim to produce dark matter particles in the lab, offering a direct way to study them. While no definitive evidence has been found yet, these experiments continue to refine our theories and narrow down the possibilities. Space-based observatories are also playing a crucial role in the search for dark matter. Missions like the European Space Agency's Euclid Telescope and NASA's upcoming Nancy Grace Roman Space Telescope will map the distribution of dark matter across the universe with unprecedented precision. By studying how dark matter bends light from distant galaxies through gravitational lensing, these missions could provide critical insights into its behavior and influence on cosmic structures. Another exciting development is the exploration of alternative detection methods, such as quantum sensors and ultra-cold atomic systems. These cutting-edge technologies offer new ways to probe the faint signals of dark matter, potentially revealing clues that have remained hidden until now. As these technologies evolve, they could open up entirely new pathways for discovery. The future of dark matter research is filled with potential, driven by a global effort to uncover one of the universe's greatest mysteries. While the answers remain elusive, The relentless pursuit of knowledge keeps us moving forward, fueled by curiosity and the promise of groundbreaking discoveries. As we continue to explore, we may soon find ourselves on the brink of unlocking the secrets of dark matter, reshaping our understanding of the cosmos in ways we can only begin to imagine. Next, we'll reflect on the philosophical implications of dark matter and what it means for humanity's place in the universe. As we venture into the realm of philosophical inquiry, the mystery of dark matter invites us to reconsider our understanding of the universe and our place within it. This invisible substance, which makes up about 27% of the cosmos, forces us to confront the limits of human knowledge and the vastness of the unknown. What does it mean that most of the universe is composed of something we cannot see, touch, or fully comprehend? Dark matter challenges our reliance on observation and measurement, reminding us that there are forces at work beyond our current understanding. It raises profound questions about the nature of reality and whether the universe operates by rules we have yet to uncover. For centuries, humanity has looked to the stars for answers, but dark matter reveals that the cosmos is far more complex and enigmatic than we once imagined. It underscores the humility required in the face of such mysteries, urging us to remain curious and open to new possibilities. At the same time, the pursuit of understanding dark matter reflects humanity's enduring drive to explore, discover, and make sense of the universe. It shows that even in the face of the unknown, we are compelled to seek answers, pushing the boundaries of science and philosophy alike. As we grapple with these questions, we are reminded that the universe is not just a place to be studied, but a source of wonder and inspiration. Dark matter, in all its elusiveness, invites us to ponder our role in the cosmos and the legacy of exploration we leave behind. With these reflections in mind, we move toward the conclusion of our journey through the 25 mysteries of the cosmic dark matter era, bringing together the threads of discovery and inquiry that have shaped our understanding of this profound cosmic phenomenon. As we bring our exploration of the 25 mysteries of the cosmic dark matter era to a close, it's clear that this invisible force continues to defy our understanding, leaving us with more questions than answers. From its elusive origins and mysterious composition to its role in shaping the universe and its complex interactions with ordinary matter, dark matter remains one of the greatest enigmas of modern science. Each mystery we've delved into, whether it's the strange behavior of dark matter halos, its influence on galaxy formation, or its potential connection to quantum physics, highlights just how little we truly know about the cosmos. These unanswered questions remind us that our journey of discovery is far from over. The universe, as vast and intricate as it is, holds secrets that challenge us to think beyond the limits of our current knowledge. Dark matter, in all its invisibility, serves as a humbling reminder of the boundless wonders that await us. As we continue to push the boundaries of science and technology, the mysteries of the cosmic dark matter era inspire us to keep searching, learning, and imagining. So, let this be an invitation to you, our curious viewers, to stay engaged with the marvels of space and science. The universe is a treasure trove of mysteries waiting to be unveiled, and your curiosity is the key to unlocking them. Don't forget to subscribe to our channel for more deep dives into the cosmos. Like this video if you enjoyed it, and hit the notification bell so you never miss an update. Together, let's keep exploring the infinite wonders of the universe. The journey is just beginning.